done in collaboration with the KIT, with the group of Manuel Salas. And yeah, the title of it is Towards Covalent Adaptable Microstructures by Combination of Two-Photon Laser Printing and Alkoxy-amine Chemistry. Yes, and I will give you first a short introduction about alkoxy-amine chemistry, then about covalent adaptable networks, and then about our printing technology we used here, and then about the project. So, alkoxy-amine chemistry. I believe all of you know the alkoxy-amine bond, and that it is a reversible bond, and it features this dynamic equilibrium between the alkoxy-amine state and the nitroxide radical state. It's a stabilized radical, and here the C-centered carbon radical. And based on this equilibrium, the alkoxy-amine bond is able to show dynamic behavior and living characteristics. Regarding the dynamic behavior, we have this nitroxide exchange reaction. You can imagine it this way. We have rest-1 connected via the alkoxy-amine bond to the nitroxide unit. And by adding another nitroxide, for example, tempo, and by making use of this equilibrium and with heat, we can exchange the nitro as a discomponent, this alkoxy-amine component, on the rest-1. And this is quite useful for covalent adaptable networks. The living characteristic is best displayed by the nitroxide-mediated polymerization, controlled radical polymerization, quite famous, I believe all of you know it. Here you see a simple mechanism of it. Okay, and yes, these reversible bonds, like these alkoxy-amine bonds, are very useful for covalent adaptable networks. Usual, normal covalent networks have static covalent crosslinks. In case of covalent adaptable networks, we have polymer networks including reversible covalent crosslinks, and they allow chemical response towards applied stimulus such as heat or light. And they have many promising properties such as recyclability, healability, shape changes, or tunability. This work here will focus most on tunability. And with tunability, we mean change in mechanical and chemical properties due to the possibility of this covalent network, covalent adaptable networks, to incorporate other chemical functionalities by post-polymerization. Yes, and when we go back to the alkoxy-amine chemistry, there are several reported systems, temperature and photoresponsive, which use alkoxy-amine chemistry. However, no CAM was printed yet. So we want to fill this void, and we want to fill this void at the micro scale. Good. Yeah. And for this, we use again two-photon laser printing, because here we have the chance to get the highest fabrication precision from tens of nanometers to micrometers, depending on your ink. And yeah, just to visualize again this multi-photon process that we have applied the picture, you see here on the bottom right, fluorescent medium and a one-photon laser, and you see absorption, successful absorption, and fluorescence during the whole laser path. And for two-photon absorption, we just have successful absorption and fluorescence in this very small focal spot. So just there we will have successful solidification, polymerization. And here you can see how this printing process works in general. And as you can see, we can also write because of that, it's also called direct laser writing. Good. Now back to the project. So when we started with this project, let's say we did again literature research, and we found out, we saw that in many disciplines like biomedicine, microoptics, microfluidics, or microrobotics, there's a necessity of microprinted structures featuring highest fabrication precision, plus custom adaptability of properties for respective applications. So, for example, adjustment of mechanical properties. And we wanted to fill this void by combining the concept of covalent adaptable networks together with alkoxy-amine chemistry and two-photon laser printing. So we started the project, we defined our aims. We wanted to prepare a 2PLP ink, which allows the formation of covalent adaptable microstructures based on alkoxyamine bonds. And the next step, we want to make use of the dynamic and the living characteristics, which we incorporated into this comes. With dynamic, we mean we want to change the cross-linking density by the nitroxide exchange reaction. And by living, we want to do a network extension employing NMP using ink extrinsic monomer. Yeah, and here's a visual depiction of our approach towards a dynamic and living 2PLP system. First, we have our ink, a liquid system, which has this tempomethacrylate moiety, this nitroxide source in it. We print it. We form our CAM network, which includes this alkoxyamine bonds. And then we can do the post-printing modification. On one side, we have NER using tempo to cleave these alkoxyamine bonds here between the different parts of the networks and to get a new alkoxyamine bond there with tempo. So we would reduce our cross-linking density in our network. And on the other hand, we want to do this chain extension by NMP using styrene and incorporate polystyrene into our network and change in this way the mechanical properties. Good. First step was to find a suitable formulation which was printable. For this, we found evaluated different ink components and found a system consisting of 4 components. The photoinitiator was D2C. It is a well-known, efficient photoinitiator for multiphoton absorption. As nitroxide source, we used tempomethacrylate. This combines, on the one hand, a methacrylate functionality to incorporate it into the network, which we polymerize, and a nitric oxide function to form alkoxyamine bonds during the printing process. As base monomer, we use the cross-linker PECTA 700, which is often used cross-linking 2PLP. And we also needed a bit of solvent, DMAC, to solubilize DTC and tempomethacrylate. Okay. Then we tested the printability. We found quite good printability at a scan speed of 2,500 bankmeters per second with a laser power of around 48 milliwatt, which is quite high. The main reason for this is the inhibition due to the tempo radical. But yes. And we were able to print, again, different structures with different complexity, and we were inspired this time a bit by nature. We printed a gecko, an octopus, and a flower-like structure. And you can see the quite good quality of the printing by the small features. You see here the feet of the geckos, the eye, or the arms of the octopus, or the inner part of the flowers. And again, this was very important for us, we found no micro bubble formation during printing. So we had, again, a very stable printing process. Good. Having now the conditions and the formulations for printing, we printed blocks of it with these optimized printing parameters, and we wanted to characterize them to find out if we incorporated this alkoxyamine bonds into our system. We did it via TOF-SIMS, and here you can see the specific ion signal for the alkoxyamine bond in the TOF-SIMS for the CAM. In case of the reference, you don't see it, so it's a clear indication that we have incorporated it. Next step was then the nitroxide exchange reaction. This was done in the excess of tempo. And here we expected an increase of this ion signal for the alkoxyamine bond and also a reduction in cross-linking due to the mechanism. Okay. And by characterization via TOF-SIMS, we could show the signal intensity increase. You can see it here, the red line for the CAM-NER and the blue line for the CAM-N for the normal CAM. And by nano-indentation, done again by Dr. Maximilian Hackner, we could show a reduction in cross-linking because we have a reduction in the mechanical properties of about 50%, which you can see here. The reduced Young's modulus at the beginning for the CAM was around 14 megapascal, went down to around 7 megapascal. The same trend for the hardness. So in this way, we could show that the NER was successful and we can reduce the mechanical properties successfully and adjust them. Okay, motivated by these results, we started with the chain extension by nitroxide mediated polymerization. And yeah, we did the NMP with styrene as ink extrinsic monomers. This had two reasons. On the one hand, it's a well-known monomer for the NMP reaction. And on the other hand, it would be also give us a drastic change in material properties. We would go from soft PECDA700 to stiff polystyrene. Yeah, and as you can see here from the IR spectrum, we have all the relevant bands and segments for polystyrene in our modified structure. So we successfully incorporated it. And you even see it better here in the tungsten spectrum. The CAM NER, and the reference showed no tryptyllium ion peak. This is a specific signal for styrene and polystyrene. The CAM NP showed quite large peak, quite intense signal. So we could successfully incorporate ink extrinsic monomer into our system. So in the next step, we also wanted to know how did the mechanical properties change, and Dr. Maximilian Hackner did again an annotation for us. And yeah, what we got was remarkable. We were very happy about this. You could see we have the CAM, and we were here around 14 megapascal with the reduced time modulus. After 2 hours of modification, we were at 2.6, 2.7 gigapascal in the reduced time modulus. The same trend in the hardness, so we were able to increase the mechanical properties by 2 orders of magnitude. And simultaneously with this, we could also increase the structural volume with higher reaction times. So here we have the structure of the CAM at the beginning. After 2 hours NMP, yeah, quite large. And after 4 hours, yeah, even larger. So it's interesting how it grows. Good. Yeah, now that we have, after we realized this, saw this, observed this, we wanted to know how do our more complex structures react with the CAM NMP post printing modification. Yeah, and we applied it on them. We did it on the flower and on the gecko. And then after 2 hours NMP, you see, yes, a structural growth. And after 4 hours, also structural growth. So very large structures in the end. It was a dramatic volume increase, to summarize, about 8 times in total. And what was very nice is that we could maintain all the fine structural features of our initially printed structures. So, I mean, you can see here in the middle of the structure, when printed, very fine features, and they maintain, they just grow. The same for the gecko, the feet or the eyes and the growing. And you see the gecko after 4 hours is almost a perfect copy of the gecko at 0 hours, at the starting state. Yes. And I mean, all the pictures were done with the same magnification unit, so you can do a direct comparison. You even see here the feet, the footprint of the initial gecko. Okay, so to summarize this part, we successfully developed a novel 2PLP ink, allowing, on the one hand, precise fabrication of 3D covalent adaptable microstructures by 2PLP, and also adjustment of the mechanical properties by post-printing modification via NER or NMP. And I just want to point this out, especially in the process with NMP and styrene, we were able to increase the mechanical properties by 2 orders of magnitude, and we were able to increase the volume about 8 times. And yes, in principle, this modification should be possible. We have every monomer polymerizable with NMP, so it should be possible to add different functionalities towards your initially printed structure, or make them less hard, or a bit more hard or softer. So we think this approach is quite useful for the future. And we're also happy that the paper got accepted, and hopefully it will be soon published. So thank you. So I'm at the end of my presentation, and yeah, I want to thank my whole group, and especially Professor Dr. Blasco for all the support. want to thank my collaborators, the University of Heidelberg, and the funding partners. And I also want to thank you for your attention. Thank you.